Black Pearl Audio Papers presents Status of Panspermia and Transpermia Theories. The idea that life might be transported between planets across outer space was championed by Svante Arrhenius about 100 years ago. Arrhenius envisaged microbes in the atmosphere of a planet being propelled by the pressure of starlight until they reached velocity sufficient to escape from their planetary system altogether. If this were to happen in big enough numbers, there is a chance that a fraction of such expelled microbes might encounter a sterile but congenial planet elsewhere and seed it with life. By implication, that is how life began on Earth, according to this theory. The panspermia theory makes no attempt to confront the problem of life's ultimate origin. It merely shunts it off to elsewhere. There is no reason why panspermia cannot be combined with the assumption of multiple geneses of life, but the main attraction of the theory is that it would permit the universe to be teeming with life even if biogenesis was a unique event. Panspermia has had few supporters in recent years, with the notable exception of Fred Hoyle and Chandra Wickramasinghe. The main objection to the original theory is that the radiation environment of space is lethal to almost all known organisms. Hazards include solar and stellar ultraviolet, solar and stellar flares, and cosmic radiation. Although examples of remarkable radiation resilience have been reported among certain terrestrial microbe species under special conditions, it remains true that all organisms would die quickly if exposed to direct solar ultraviolet, and more slowly, but still fast compared to interstellar transit times of millions of years, from cosmic radiation. It is possible to concoct elaborate scenarios in which microbes ejected from a planet are afforded a measure of protection from radiation, e.g., by coating in dust, immersion in an interstellar cloud or comet, enabling them to survive long enough to reach another star system. But such rare concatenations of events would not serve to provide a common dissemination mechanism to populate the galaxy, let alone to permit transits across intergalactic space. So whilst it may be the case that, here and there, one planet has seeded another in a neighboring star system, a pervasive panspermia mechanism seems extremely implausible on current evidence. The foregoing objections are largely circumvented, however, in a different scenario known as transpermia. In this theory, microbes are transported between planets cocooned inside rocks, which offer a measure of radiation and thermal protection. Impacts by comets and asteroids with rocky planets are known to displace large masses of material. Theoretical studies by Mileikowski et al. Indicate that a substantial fraction of rocky ejecta would be displaced into orbit around the Sun or parent star without suffering lethal shock heating. Some of these displaced rocks will eventually strike other planets and could thereby seed them with life. This is an old theory. Its essential elements were articulated by Kelvin as long ago as 1871. Transpermia would be a very efficient mechanism for transporting life between Mars and Earth, and to a lesser extent, vice versa. Computations by Gladman et al. Show that 7.5% of Mars ejecta will hit Earth eventually. Most microbes could withstand the G-forces associated with impact ejection. The vacuum conditions and low temperatures of outer space need not prove lethal, as freeze-drying bacteria and archaea can actually increase their longevity. High-speed atmospheric entry would present the hazard of incineration, but rocks entering Earth's atmosphere at shallow angles would not invariably vaporize. Fragments could reach the ground intact, and with short enough atmospheric transit times to prevent heat penetration to the interior. Mileikowski et al. Have studied the radiation and thermal damage hazards to dormant bacteria and spores in this scenario, and determined that viability times of order millions of years are not unreasonable. This is easily long enough for live bacteria to make the journey from Mars to Earth. The foregoing considerations make it almost inevitable that Mars and Earth will have cross-contaminated each other repeatedly during astronomical history. Mileikowski et al. Estimate a traffic of about 4 billion tons of unshocked Martian material unheated above 100 degrees Celsius, reaching Earth over the last 4 gigayears, and a smaller but significant amount going the other way. Given that Mars was warm and wet at a time when life is known to have existed on Earth, the seeding of Mars by terrestrial organisms seems very likely. The reverse is also true. In fact, a good case can be made that Mars was a more favorable planet than Earth for life to get started, raising the possibility that terrestrial life began on Mars, say 4.4 billion years ago, and spread to Earth subsequently. The key point about transpermia for the discussion in this paper is that it comprises the chances of finding a second genesis of life on our nearest neighbor planet. If traces of life are found on Mars, it seems very likely that it would represent a branch of Earth life rather than an independent origin. The probability of contamination by Earth and Mars rocks diminishes sharply with distance, so there is a good chance that Europa is free of this problem. Transpermia would be a very inefficient mechanism to propagate life between star systems, as the probability that rock ejected from Earth or Mars by an impact will hit an Earth-like planet in another star system are negligible. The conclusion is that if biogenesis was a unique event, we might expect life to have spread beyond its point of origin to near neighbor planets, but no farther. If evidence for life were found outside the solar system, e.g. by detecting ozone in the atmospheres of extrasolar planets, it would provide strong support for biological determinism, with its implication of optimal biophilicity. This concludes Section 2 of How Biofriendly is the Universe by PCW Davies. Please stay tuned for Section 3.